Hello and welcome back. Uh, 2023 is finally here. We're going to be looking at day one today. This is probably the most difficult day one that I think I've seen so far in Advent of Code. So, kind of interesting. Let's dig into it. So, there's a bunch of flavor text, um, kind of interesting, but we'll get to the meat and potatoes of the problem here. Basically, your problem input, you get a series of lines. And these lines have a bunch of garbage text, but they also have digits in them. Um, and the problem asks us to basically pull out the digits. So there's some parsing here. And then once we pulled out the digits for each row, we combine the first digit and the last digit, kind of not by like addition or multiplication or anything, but so like if you had a 2 and a 7, those combined would be 27. So you combine those into a two-digit number. And then once we have all of the two-digit numbers for each row, then we add them all together, and that will give us our part one answer. So we can get started with that. And I am back in APL for this one. So my APL brethren, we are back. Might do some videos in other languages as well throughout the event this year, so stay tuned. But yeah, so first we'll get our problem input. This is just ingit 2023-01.txt, and that gives us all of the lines. And we'll assign this to P. Now, when we're thinking about how we want to solve this, there's a bunch of different ways that you could do it. So APL does have support for, it has full regex support via quad S for searching and quad R for replace. I think, to be honest with you, I haven't really used regexes that much in APL. But we're going to try and solve this as much as possible just using normal APL primitives. And so what would be cool to do is to, we can pull out all of the digits, and then either we pull out the digits themselves, or we keep the length of the array, or the length of each vector, and we have some sort of like filler element so that we're able to keep the shape. And I'll tell you right now that keeping the shape is going to be useful for part two. Something very interesting about the input. So if we enlist our input, so we just get a vector of all the characters, and then we see if there are any zero characters in there, any digits that are zero. That is not the case. So zero never occurs in the input. And what that means is that we could, if we can construct a vector where like zeros don't match any digits, and then the digits are just there, that allows us to keep everything in numeric form, which makes it easier for adding everything together and things like that. So we also have quad D. Quad D gives us a string with all of the digit characters. So this makes it super useful for these problems where you're sort of like parsing strings for digits. Let's look at the first row of P, and then let's say that we take quad D, and we find the index of all of the elements in P. We get a vector like this. So now index of, if the element in the right array is not found in the left array, it will give you an index that's out of bounds of the array on the right side. So the first thing that we're going to do, because we are in the default index origin of 1, we're going to decrement everything. So we'll just do -1 plus. And then all of these 10s here basically represent non-matches, so they're non-digit characters. So we can just do 10 mod to wrap all of those back around to 0. And then we get this sort of vector, which again, if you look at the first row of P, we can see that we've successfully pulled out the 9 and the 7, and those are in place in our numeric vector here with zeros where everything doesn't match. So this is going to be useful. We can do this for every element of P by binding quad D to the index of function here, and then doing it for each row in P. And that gives us this, and we'll assign this to like D for digits, I guess. Okay, so we need to, first of all, we need to figure out where the real numbers are in each vector, and then we need to take the first element and the last elements and combine them together, right? So for each D, the first thing that we're going to do is we are going to remove, so we'll use without here, we're going to remove all of the zeros. Now, if you're doing this in tacit form, it's important to note, I got burned by this, and someone on Reddit commented that you can do things this way. Normally, you cannot have a literal as the last value in a train for some reason. There's a good explanation for it, but I forget what it is. So you can't write the train like this. You'll get a syntax error. So it's got to be like this. This removes all the zeros. You can see that we have only the real numbers here, and then we'll run another train on the resulting value, and we want the first value concatenated with the last value, and this right tack reduce will give us the last value of a vector. So we do that, and then we just need to combine them together. Now we could like format these into strings and concatenate them and then eval them back into a number. But because we know that each one of these are single digits, we can just do 10 decode. Decode is super useful for converting from like binary vectors into numbers, things like that. So 10 decode basically treats these as base 10 vectors. So the first digit will be in the tens place and the second in the ones place. And that will, actually, let's move this inside here. There we go. And that will combine all the numbers together, and then we just have to add them up. And that gives us 55, 44, 7, which is indeed our answer for part 1. So we can also make this a function, a tacit function, and then if we run f on our digits, we'll get the same answer. Splitting this out into a function is going to be useful because we'll reuse it in part 2. Speaking of part 2, this is where a lot of people got tripped up. If you're just using, well, so first let's look at the problem. Basically, it says, oh, we're not actually just looking at literal digit characters. The digits can also be spelled out as words. So 1 through 9, all the different words also count as digits. So when we're constructing the vector of meaningful digits out of these strings, we have to take into account these words. And the problem is that there is overlap in the words. So like this 8 and 2, when you're constructing the vector of possible digits out of the string, you have to have both 8 and 2. And you can see this happen with like twone, 2, 1, 9, 8, although we're using this. So a lot of people are using like regexes, and the problem with regexes is that they consume, if you're not using like look-aheads, I think I'm no regex expert, but it'll consume the string character by character, and that means that like if you're matching against this, it'll match 8, and then it'll start matching again on WO, and you won't get the 2, right? So just be careful of that. Now, as I said, we're not going to be doing regexes. We're going to be using APL functions. So let's see how we can do that. First, I think that it makes sense to have a vector of all of the words that we're going to be matching against. So here we go, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we can split all of these on spaces by using the partition function. So that gives us all of the different words that we're going to be matching against. And we'll assign this to n for like numbers, I guess. And other than that, we're going to be heavily using this. This is a nice function to be aware of in APL. It's called find. Basically, what it does is given a large array on the right and a subarray on the left, it will give you a Boolean array where the ones mark the start of the subarray in the larger array. So you can see the example here with Anna and banana. You can see where the substring Anna starts, and it can even be used in higher rank arrays with matrices and so forth. So for example, if we look at the first row of our input, just looking at this, it looks like we have a 7 in here that we'd like to match against. And so if we do like 7 find, we will get a 1. So it found a match and it's putting it in the location where the match starts. And if we want to do this for all of our words, we can use outer product. So rather than 7, we can use our vector of all our different words. And we use an outer product, and we'll enclose P to make sure that we have the right shape here. And then I'll mix this so we can see it easier. So the way to think about this is each one of our rows is one of our words, and then each column denotes whether or not that word has a match that started at that location. So we have a 1 here, and actually if we look at, we can look at like where to get the index of that 1, and we can see that it's on the 7th row. So out of our vector of words, we had 1 match on the 7th row, right? And what would be really cool is to reduce this matrix down so that we have, we have a vector of where zeros constitute a non-match, and then the numbers are the actual digits that get pulled out, just like we have for, D, if you look at this. So what we can do is, it would be cool if let's say that we generated the numbers 1 through 9, and then for each row, we multiplied by that, the number in that range. So like we'll multiply 1 by a bunch of zeros, 2 by a bunch of zeros, and then we'll multiply 7 against this row with the 1 here, and that will turn it into a 7. Everything else will remain 0 because anything times 0 is 0. And then once we perform that multiplication, we want to add all of these rows together, and that will give us the digits that got pulled out at each location. And we can do that by using inner product. So we can say iota 9, which will give us the range from 0 to 9. Sorry, we're in index 1, so it'll give us the range from 1 to 9. And then we do plus dot times to do a vector matrix multiplication. And you can see here that it pulled out the 7. So let's look at the first row of the input again. So it pulled out the 7 in the relevant location, exactly where the match starts. And then if we want to, so problem 2 says it's not just the words, it's also the digit characters, but we've already parsed out the digit characters. So we can just say, like, let's take the first row of D and add it. And now we have 9, 7, and 7. And if you look at the first row of P, you can see that we have a literal 9 character, the word 7, and then 7. right? So this parsing seems correct. And then we can extend this to run on every row in P by just removing all of these firsts and encloses. And then in this form, we can run our function f that we defined before, and that gives us an answer of 54,706, which is our answer for part 2. So we sidestepped a lot of the overlap complexity. I saw people doing like string substitution, where they like substitute the word with the literal digit inside it, stuff like this. We sidestep a lot of this by just looking at each one of the words and performing matches individually, keeping the order that they appear in the vectors and adding them all together. Yeah, we just used APL primitives, so no regexes or anything. We put it all together. It looks like this. Oh, this one line is... An interesting challenge might be, can you generate this string? Can you generate this string without actually typing it in? Save some characters. I think that's... I'm not sure if you can compress this or not, but anyway, this is the solution. 5 lines, just using APL primitives. And the runtime complexity is a little bit weird because we're doing outer product here, so it's like an n squared thing. But the size of the input, it doesn't really matter. So that is part 1, and yeah, excited to be back in the season. Stay tuned, and I will likely post some more videos about the upcoming problems. All right, talk to you later.